Good morning, good afternoon, good evening, everybody. Thanks for joining this session, SQL Server Memory Internals and Troubleshooting. I'm very thankful to the Data Saturday team, specifically Podinen team, Marco and all his colleagues for giving me this opportunity to present this session for all of you. My name is Amit Bansal. I work for SQL Maestros, and as Marco mentioned, I also do a lot of community stuff with Data Platform Geeks, SQL Server Geeks, and Data AI Summit. Now for you, most important stuff here is the first URL that you can see here, event session and resources. It's a bit.ly link. Maybe at the end of the session, I can probably put down the URL so you can download the deck and the resources, the code snippets that we are doing. But if you don't want to just remember all these bit.ly links, just go to sqlmaestros.com and everything is right on the homepage, the resources, the events, etc. And you can download a copy of the presentation and resources. I'm on Twitter, _Bansal. So here is a very quick overview of my work. I am MCM for SQL Server, also an MVP for a couple of years, and Microsoft has also honored me with regional director status. At SQL Maestros, I do a lot of stuff, consulting, training, performance tuning stuff, health check, and community front, I did mention Data Platform Geeks, SQL Server Geeks, and Data Platform Summit. So let's get started with the session now straight away. Warning, first warning for all of you about SQL Server Memory internals and troubleshooting is that do not expect that this session is going to make you an expert in troubleshooting memory issues with SQL Server. If you are kind of new to memory area or memory troubleshooting, then this can serve as a level 200, 300 overview. It's not going to dive very deep into the memory architecture or troubleshooting scenarios. And also because we just have 60 minutes to be precise, there's a lot of information that I am going to cover. But this is going to give you a very good head start into SQL Server memory architecture and how should you approach troubleshooting. What are the important DMVs? What should you be looking for? Those are the kind of things that you will get from this session. So we are not going to talk about everything related to SQL Server memory architecture. We are not going to talk about all possible memory scenarios. There are a bunch of perfmon counters and DMVs. We are not going to talk about all of them. So the question is, what are we going to talk about? Well, things that we are going to talk about is briefly, very quickly understand NUMA architecture, which is non-uniform memory access. Then I'm going to touch upon SQL Server Memory architecture, and I'll give a level 200 overview, because before we go deep into troubleshooting, we need to understand how SQL Server Memory works. How does it interact with Windows? So that knowledge and that background information is important to the extent that it helps us in real world troubleshooting. To satisfy our intellectual curiosity, we can just keep going deep and deep and deep, but beyond a certain point, it may not really help with practical troubleshooting. One of the important takeaways for you in this session is going to be, how do you track memory usage? This is a very constant question that keeps coming on forums, that my SQL Server is consuming 95% memory, it's choking memory, and I see it hogging up all the memory that I allocate. So where exactly is the memory being consumed, and how are you going to track that component wise? That's going to be a very important learning. We are going to look at certain memory pressure examples, and hopefully I will be able to complete at least 2 scenarios where I will show you out of memory errors and how you can track where the problem is. And of course, loads of demos along the way. So better understanding of SQL Server Memory, how it works, and how do you approach troubleshooting. These are the 2 important things that you're going to take away from this session. And I'm just going to cover it in a very, very simplified way. So let's get started. First, symmetric multiprocessing systems. Back in the days when we had a computer, let's say a server with multiple CPUs, and in this diagram you can see that there are 4 CPUs, but back in the days with 1 CPU, 2 CPUs, 4 CPUs, when CPUs need memory, right, to do their work, they would access the memory controller. So they would access the physical memory via the memory controller. But in this hardware design, in symmetric multiprocessing hardware design, you have a single memory controller, and all CPUs are going to talk to this single memory controller via which memory allocations are going to be done. Now, until let's say up to 4 CPUs, things were all good. But when you have more than 4 CPUs, and let's talk about today's world, or at least a few years from now, when you had like 8 CPUs, 16, today's systems have like hundreds of cores. And think about like 500, 600 cores accessing the memory controller. There's going to be a lot of contention at the memory controller, and the access to physical memory is going to be very, very slow. If CPUs don't get the memory they need, their operation, their performance is going to come down drastically. Here comes a very important design called non-uniform memory access, and this is today implemented by default in all hardware topologies and all hardware architectures. And in a very simplified overview, what exactly is this design? The physical memory is bifurcated. So let's say you have a server with 32 GB RAM. It's going to be physically bifurcated. It's not a logical division, it's a physical division, though it can be customized logically using soft NUMA, but that's out of scope of this session. So this hardware design is going to be physically bifurcated into separate NUMA pods, which means 32 GB is going to be divided into 16 GB, and you will have 2 pods of 16 GB each, or rather 2 NUMA nodes of 16 GB each, and each NUMA node will have its own memory controller. So we can talk about NUMA node 0 and NUMA node 1. Now, because physical memory is divided by 2, let's say NUMA node 0, NUMA node 1, then even CPUs are going to be equally distributed to these NUMA nodes. So in this example, let's say this hardware had 8 cores or 8 logical CPUs. Now, they are equally divided 4 each to the NUMA nodes. So if you look at the first NUMA node, node 0, the 4 CPUs there, let's say from 0 to 3, will access the memory that is available in NUMA node 0. It has its own memory controller. That is where contention is elevated. And NUMA node 1 has its own 4 CPUs numbered from, let's say, 4 to 7, and it has access to its own memory controller and to its own physical memory, the other 16 GB. Now, they are interconnected, which means at any point of time, if CPUs need more than 16 GB, they definitely can have access to more than 16 GB via a physical interconnect. This is a very simplified design that you see in front of you, but actual NUMA design can go pretty complicated, and there are different architectures also in NUMA. So you can have like 16 nodes, 32 nodes, it could go that big. So as you scale up, you can see complex designs and architecture. But end of the day, there's one thing that NUMA helps. There's only one objective, which is faster access to memory. And SQL Server components need memory, right? Buffer pools, the optimizer, the plan cache. There's so many different components inside SQL Server that need memory pretty quickly, right? And faster access to memory is very critical. So NUMA solves that problem, right? So keep that in mind. This is just a background information about NUMA. Now, let's talk about the guiding principles of SQL Server. So before we go into the depth and look at all demos, first guiding principle of SQL Server Memory is dynamic acquisition and freeing of memory, mostly automatic. Let me just move this GoToMeeting tools here so that they don't block the slide. Okay, sorry, this is better. Thank you. So first guiding principle is dynamic acquisition and freeing of memory, mostly on automatic. So SQL Server Memory is mostly managed automatic. You have a few knobs and switches to control a few things, but mostly it is automatic, and nothing allows you to go very deep and have a very fine-grained control over SQL Server Memory. That's the first thing. Second, minimize physical I/O, maximize buffer pool. That is the objective of SQL Server. Physical I/O is slow. SQL Server wants that there is most of the times there is logical I/O, which is it wants to read from memory. So the more memory you allocate to it, it will consume all of it and try to cache as much as it can. That is the kind of algorithm the buffer pool has. Then comes keep a check on buffer pool size to avoid system-wide memory pressure. Now, if you look at point 2 and point 3, they're kind of contradictory. On one side, we talk about minimizing physical I/O and maximizing buffer pool. On the other side, we want to keep a check and buffer pool as well, because buffer pool turns out to be the biggest memory consumer, and you don't want it to be so big that it pressurizes other memory consumer. So it kind of, the database engine has to do a balancing act there. Lock pages in memory. SQL Server would love that pages are logged in memory, because when they're, for whatever reason, you don't want those pages to be, let's say, spilled down on disk. And if that happens, the memory access again is going to be slow. And we're talking about the memory pages here, the buffer. Min and max memory settings. There's a whole lot of guidance available on internet about min and max. And in quick summary is, you should always put a value for min as well as max. Let's say if you have 16 GB of memory, you leave something for Windows, something for threads, something for external processes, and maybe tools and applications that are running on Windows, and assign a decent value to SQL Server, let's say 11 GB or 12 GB. So max is important, so that you don't want SQL Server to pressurize Windows. That is one. Minimum. If you set a value for minimum, you will ensure that SQL Server memory does not go below that min value. So it stays between min and max. That's the kind of basic architecture about min and max. Also remember that max now, in terms of memory settings, is more or less the actual max for SQL Server, but it does not take the direct Windows allocation into account. It does not take CLR. It does not take the thread access. So there are a few things that are excluded out of max, but then mostly it is max. Prior to 2012, max used to be only the buffer pool memory, but then that architectural change was done from 2012 onwards. There are these memory consumers, as I talked about, buffer pool, the caches, the query workspace memory, etc. And yes, memory is bifurcated by NUMA. So even in SQL Server, when SQL Server boots up, it will read the NUMA information from Windows registry and will reconfigure itself based on the NUMA design that you have put. Two types of memory pressures that are there in SQL Server: internal and external. Internal memory pressure is caused by internal workloads and components, and there are certain memory pressures that are external factors outside of SQL Server. So maybe you have some kind of tools or apps that are running on the same server where the SQL Server is installed. That's kind of termed as external memory pressure. Another guiding principle: don't try to compute every number. You will never get it. What I mean by that is, when I am going to use all these DMVs, and even when you try out the code, and I'm sure you must be playing with DMVs, it's very overwhelming, the kind of attributes that are there and so many numbers that keep flying around. It's kind of very difficult to find out the mathematics and algorithms behind all of that. But yeah, mostly you will get it, but there's no point really trying to decipher or decode every calculation that you see out there. Last but not the least, when speakers talk about SQL Server memory, they sometimes say wrong things and their demos may not work. Keep that in mind. Okay, that's a very important guiding principle for this session also. So let's welcome all of you to the dungeon, SQL Server Memory, which is CCC. What is that CCC stands for? That is confusing, complicated, and convoluted. That is SQL Server Memory. Let's get started with a little bit of architectural stuff. So what you see on your left-hand side is the physical RAM. So I'm not talking about SQL Server at this point. Physical RAM, you have, let's say all these are the memory pages. You can track the physical RAM, the amount of memory your server has, using two DMVs, which gives you information. One is DIMM OS process memory, and the other one is DIMM OS system memory. So as you see, there is slight difference between the two. The sys memory will give you system information about the box, the hardware, and OS process memory will give you information about the SQL process itself. And both of these DMVs come under the SQL OS operating system, and that's why they're categorized under OS. So that is physical RAM. Now comes the NUMA nodes. We have still not come to SQL Server. So what happens is, assuming that you have this SQL Server deployed on a server with 4 NUMA nodes. So these yellow, orange, whatever that color is, orange boxes represent NUMA nodes. And I have shown 4 NUMA nodes here. You can track all the NUMA nodes and get NUMA configuration from a DMV called sysdm OS nodes. That will give you Windows low-level node information. So remember, we're still talking about at the OS level. Now comes the memory nodes in SQL Server. So as SQL Server boots up, it reads the NUMA configuration that is deployed with Windows. Maybe someone could have implemented even soft NUMA and re-architected NUMA, and whatever that is, it will read that information and it's going to present the memory nodes to you using a DMV called sysdmos memory nodes. Now this is going to give you how SQL Server is seeing its own memory nodes, and in most cases you will see there is going to be a one-to-one mapping. So you're going to see, because there are 4 NUMA nodes at hardware level, there will be 4 memory nodes inside SQL Server, 0, 1, 2, and 3. Now let's take a step back. What do we mean by memory nodes in SQL Server? So everything that SQL Server does now, memory allocation, memory management, it is all going to be node wise, which means if you remember all these background processes like resource monitor, checkpoint, lazy writer, so on and so forth, they are all going to be node wise, which means if there are 4 nodes, there will be 4 resource monitors, there will be 4 lazy writers, there will be 4 checkpoint processes, because all of them have to deal with memory. And as I said, they're going to deal node wise, right? And that's the beauty of the architecture here. Inside SQL Server now, everything that you do with memory management, troubleshooting, it all has to be node wise, and you're going to see that in the demo soon. Now, when SQL Server needs memory, it is going to talk to Windows. And how does it talk to Windows? Well, it uses Windows APIs, and there are a bunch of these APIs which are further categorized into base allocators and structured allocators. This session will not dive deep into these, but just keep that in mind that there are a bunch of these Win32 APIs that are being called, and allocation of memory from Windows to SQL Server is done in fragments and blocks. That's more important from a basic troubleshooting perspective. So SQL Server, as it needs memory, it will keep talking to Windows, and Windows will keep allocating as much as it can up to the max limit. And when we say max, it does not really mean that there is going to be hard limit. Sometimes you will see that SQL Server has consumed more than max, but then in due course of time, it does balance out. So that is something that SQL Server internally keeps a track of. And then it may happen that Windows needs memory. SQL Server has taken all of it, 90, 95%, whatever it is. And for some reason, Windows needs memory. Let's say there is an application running on Windows and it needs memory. So what it's going to do, it's going to send a low memory notification to SQL Server, and then SQL Server may release some memory back to Windows. Otherwise, SQL Server loves to keep memory to itself, in simple words. When we look at SQL Server layer, SQL Server memory architecture, we kind of can say that it's a 3-layered architecture. At the topmost layer, you can say are the nodes which are talking to Windows, and then comes the second layer, which is what we call as the clerks. And then the bottommost layer is called as memory objects, and you can see that at the bottom of the screen: memory nodes, memory clerks, and memory objects. Consider them as a 3-layered architecture. So what are clerks now? So you have nodes, and nodes are responsible for taking memory from Windows. But who is telling nodes that they need memory? Well, those are memory clerks. Now, what are memory clerks? Memory clerks are actual memory consumers inside SQL Server. But then their clerks itself do not need memory. Those are components inside SQL Server. For example, the query workspace, or the buffer pool, or the plan cache, or the optimizer, or the parse tree. There are so many components inside SQL Server that needs memory, and in most cases, these important critical memory consumers have their own clerks. When they need memory, they tell their clerks, and the clerks will talk to nodes, and nodes will talk to Windows via the Win32 API and get the memory that they need. So that's a very simplified explanation of memory clerks. So if you have a question in your mind, how do I track memory consumption inside SQL Server component wise, clerks will give you the answer. So remember, clerks actually give a lot of answers. And in one of my demos, you will see, and in fact, both the demos, you will see that I'm going to use clerks quite heavily to track memory consumption. When memory is consumed and is available with the clerk, it's just not a direct allocation. That memory is broken down into fine-grained objects, which I'll call as memory objects. So memory objects are basically the lowest level of allocations. Maybe you could say that lowest level of allocations that happen, and like let's say each memory object is at bare minimum is an 8K allocation for the overall memory that is required by the clerk. So if you really want to dive deep further beyond the clerks, you will have to go into memory objects. So memory objects are the so-called allocations that you can track. The clerks itself are divided into general clerk, object store, user store, and cache store. And the easiest example that I can give you in terms of classification of clerks is the cache stores, like the the beautiful one, the ad hoc plans, which is the SQL plan cache. So these are all the cache stores, and plan cache. Let's take example of plan cache. So that also needs a memory. So it is also a clerk, but it is classified as a cache store because it is caching the execution plans. And then it also has a limited amount of memory. So, and you have more new plans that are coming in. So there is a clock system inside SQL Server that is going to flush out the old cached items from the cache stores to make space for the new items that want to come in. And this is the clock hand system algorithm that runs. And I will not dive deep into how that works, but that is there's another algorithm called as the brokering algorithm, because it's like negotiating that, okay, I need more memory, but the cache store is full. So which are the plans that can be flushed out? For example, plans that have been least used, plans that are oldest in the cache store can be flushed out, making space for new plans to come in. So the memory brokers is the algorithm that does that negotiating job. So this gives you that overview, and of course there is this resource monitor. You can track. It's like a bird's eye view of what's going on the overall system, and that resource monitor. And so for example, if there is a low memory notification or SQL Server is under pressure, it will put an entry into this DMV called sysdmos ring buffers, and you can extract that information and trace down as to what exactly happened. So that is resource monitor, like an owl watching over what's going on with memory. And also, friends, when we talk about all this memory consumer, so if most cases, all these memory consumers of SQL Server will follow this architecture, which is the clerk talking to the node and the memory allocation happening, then the memory breaking down into memory objects, and the clock system working and the broker system working. It's fine. But there are certain allocations that we call as direct Windows allocation, or DWA, which does not come under the purview of this architecture. For example, if you are calling a DLL, if you have loaded a DLL inside SQL Server process and that DLL needs memory, it's going to be a direct allocation from Windows via the virtual address space. So that will not follow this architecture. That is an exception. SQL Server Memory itself has three memory models: conventional, locked, and large. Very quickly, if it is a vanilla installation of SQL Server, it is conventional. You have not made any change to the memory configuration, so it's kind of conventional. The moment you, let's say, turn on locked pages in memory on Windows user write assignments, it is then locked memory model. And you would know that in most SQL Server deployments have locked pages in memory turned on as well. It's not really required unless you see SQL Server memory being flushed down to disk, but otherwise it's not needed. And sometimes that's why this is also a best practice to kind of just keep it turned on. So that's the locked memory model. This another memory model which is called as the large page memory model. If you want SQL Server to take advantage of Windows large page option, where each large page could be like 16 MB, for, let's say, very memory intensive queries, large execution plans, etc., and you want contiguous memory allocation, then there is large page model. It has certain criteria. Trace flag has to be turned on, box needs to have more than 8 GB of RAM and enterprise edition, so on and so forth. So that's the quick overview and architecture of SQL Server memory, and I would, given the time, I could only spend this much on the architecture. Now is the time to jump into some demos. So let's switch over to the VM and look into demos. So I'm just seeing Yes, and if can someone confirm if the VM is available? Can you see the VM and the management studio? Thank you. So let's get started, and we'll look at certain basic things using DMVs. Some of the things that we talked about just now, let's try to put that into action, and then I'll do at least one demo of out of memory errors. So remember, we talked about this dim OS process memory, which will give you information about SQL Server process memory consumption. So if I execute this, important numbers for you to follow is right now, this VM, which I just started off, is consuming less than a GB, about 700 MB, and large page allocations is 0, log page allocation is also 0, which means this is running in conventional memory model. And okay, and this is giving me information about the nodes, how many nodes we have. This is a VM right now, so I have just one node. 64 is for DAC, so doesn't apply. So I have node 0, which is is online, and if you run this, if you just simply do a select star on your production box, you might see multiple nodes out there. And remember, this is the low level OS information. If you go one level down, you can actually see the actual memory nodes, which are of course tagged along with the OS node. So you can see that the target is about 7 GB because I have given 10 GB to the VM itself. And you can see memory node is 0, reserved is 25. So there are reasons why these numbers are allocated, but I'll talk about that a bit later, or maybe skip over all of this. But this is the important information that you need, not really OS nodes, but memory nodes, because this gives you SQL Server information. Now, target GB here, of course, means that we can go up to like 7 to 7.5 GB of memory consumption. But right now, our consumption is only 700 MB. Then comes the clerks, and in the 3-layered architecture. And if you just look at what clerk looks like, so you have these memory clerks, and look at the name of all these clerks that are there. Each represents a component inside SQL Server. And what you need to really bother about is the virtual memory reserved and committed. Then comes the objects. And now if you look at clerks, there are about 300 clerks there. And remember, clerks are also bifurcated by nodes. That's an important thing to note. So if I have 4 nodes here, you will probably see approximately 300 clerks multiplied by 4. So about 1200 clerks, one for each node. Then you have the memory objects, and memory objects talk to the, are the so-called allocations of memory via the clerk. So you can see about 3000 memory objects out there, and we have the memory object address, and there's one more component there, which is allocation. So let's see where that is. Page allocator address. This is how we can actually find out which memory objects are allocated via a specific clerk. Now, first things first, we want to see which clerks are consuming maximum memory, or which let's say buffer pool, which is one of the largest memory consumer. How much amount of memory is being consumed by buffer pool? Those are the kind of things we want to find out. So if I take up this specific clerk query, you can see, I can see that about 100 MB is right now being used by the buffer pool. So if you look at the query, we select a few columns, and we are doing it from memory clerks, where we say the type is memory clerk buffer pool. So we are trying to find out how much memory is being consumed by a specific clerk. Otherwise, the easiest thing that you could do is to see memory consumption clerk wise or component wise. We can always say order by, let's say, okay, which the column is, let's say, virtual memory reserved. Okay, virtual memory reserved. Okay, no, order by pages KB. That's what I'm going to do. So this will give me component wise tracking. Now, if you see this output here, it tells me that PHDR for bound trees, right? For parsed trees, that's consuming maximum amount of memory. Then comes for the SQL plans, and then the buffer pool, which is about 700 MB. We had tracked that. Then for extreme performance, this is for in-memory OLTP, so on and so forth. So you can see all the clerks up there. There's a clerk called SQL General, and some operations, for example, XML, when you deal with XML documents or XML data, that also needs memory. It doesn't have its own clerk, so it will you can see XML objects there in memory objects, and it consumes memory from SQL General. That's what I have seen. So there is a general clerk as well. Now you can always track down. So let's start with buffer pool. I want to start with buffer pool because buffer pool seems to be one of the largest memory consumers. You will see buffer pool as quite big because it's the largest cache of data. What does buffer pool really do? It will cache data pages. Your workloads are reading pages from disk into memory, and this is what it's going to cache. So if we want to see how much memory is being consumed in this 100 MB, what's the breakup database wise? So you can see the hidden database is consuming about 23 MB. Then you have SQL Maestros and some of the other databases. And for each database, let's say AdventureWorks 2016, how much memory is being consumed by each object of AdventureWorks, then you can see these are the tables that are consuming memory. Now, this really helps to find out who is eating up memory for all this huge consumption that is happening. Now, let's say you just saw this output where you can see in AdventureWorks 2016, some of these objects are consuming, all of them are consuming less than 1 MB. Now, let's build up a scenario. Let's just simulate a few things. I'm doing a select star from sales order header and sales order detail. They are not huge tables, just a few MBs, but I'm just trying to get all of their data into memory. Now, the moment I have done it and I go into the helpers here, and first I'll see what is the memory consumption of SQL Server right now. So you can see from 700 MB, we just jumped over to 722. So which means just about 20 MB of allocation. Now, assuming that this is a huge allocation that is happening and you want to find out who is eating up all the memory. So what am I doing now? I am just going to first go and look into the allocation of memory database wise, and I can see that AdventureWorks 2016 is like eating up a lot of memory. Then in AdventureWorks 2016, which are the tables that are being cached in memory, and I can see that sales order detail and sales order header are now right on the top. This really helps us to break down the memory consumption. So I'm going to look at the clerks, and in most cases you will see that buffer pool is right on the top, but not always. And I'm going to show you how and when, but not always. So if you see, assuming buffer pool is right on the top, and now you want to break down the buffer pool. So you're going to first look at the database, and then inside the database, which objects are consuming maximum memory. So this was just a few quick things to kind of warm up before we go into more deeper demos. Now, if you want to take one level, you want to go one level down, take a step further and try to decipher these clerks and objects. Let's take a small example, and I think time will permit. So if I have memory clerks, let's say one of the clerks is called as cache stored PHDR, which is for your bound trees, the internal query tree that the optimizer prepares. If I execute this, I can see that currently it is consuming 84912 kilobytes, right? That's the amount of memory that is being consumed by this clerk. What I can try to do is I am going to join clerks with, so where is this? Yeah, so I'm going to join clerks with memory objects because I want to see a breakdown of this 84912 kilobytes in memory objects. And the joining column, as I mentioned earlier, is page allocator address. And I filter on cache stored PHDR. So let's go and do this, and you will be able to see that these are, so there are about 481 memory objects. Look at these memory objects. All of them are memobj parse. So the clerk is PHDR, the object name is memobj parse, and this is the breakup of the cache stored PHDR. And if you scroll down, look at the page size there. Each page is about 8K. So this is the final detail at the most granular level you can find out how much and how the memory is broken up. And this does not help much, but I'm just trying to show you the architecture aspect, which means that if I actually sum up the memory consumed by each object, it should amount to 84912. Is that the number? So let's go and find out. Okay, now it is 84960. That's the number. So let's add up all the mem obj parse, right, and sum up their pages in bytes. So let's execute this, and you will see 84856. This is 84856 because there is one root object which is not named as mem obj parse. So if I scroll down just quickly to show you which one that is, maybe right at the, okay, there you go. So this is the root object which is called as mem obj cache store, and it is taking 106496. And if I can take that and add up here and execute this, you will see 84960. So you have seen how the clerk shows up 84960. Is this the number that we saw? Let's go and verify. Yes, it is 84960. And how the breakup of 84960 with about 400 memory objects. Okay. Now let's look at memory consumption, and as I said, clerks answer quite a lot. So if you select this once more, just to show you, this is how the clerks are currently consuming memory, and you have the buffer pool, which is right on the top, followed by PHDR, SQL CP, so on and so forth. Now let's create OOM exceptions and see how clerks and memory objects can help you troubleshoot. So let's go over to the first example there, and I'm opening up. Let me close down this one. So it will take me a few seconds to just do the setup, and I'm going to explain you what exactly I will be doing. Okay, let's keep this. First, let me open up all the scripts, and then we will get started. So I have helpers, I have troubleshoot, I have setmem, and I have cause OOM SQL, and I think this should be all set. Let me just quickly see what I am doing here. This is fine. Okay, that is all right. So what we will do, friends, is here is a demo where I'm going to cause a out of memory exception, and then we'll see how we can track this error and memory usage using clerks and objects. That's going to be your takeaway. Helpers.sql here, I'm keeping it on the left hand side as the first script which will give me constant answer as to where is the memory being consumed. So the first script gives me overall memory consumption. Second one will give me information about the clerk. Third one will talk about the buffer pool, and then the cache store. So so this is helpers, and then the troubleshoot is going to give me similar information, process, and then I am going and looking into memory objects and clerks. So let's go and run these three right now to troubleshoot. So what you can see at this point here is that physical memory is about 729, and you can see this information is coming from memory objects, and you can see that right now mem obj parse is right on the top, and you can see clerks buffer pool is right on the top. So let's keep this window on. So we can see that SQL Server is consuming about 700 MB or so. What I'm going to do is to create an OOM exception. I'm going to set the max memory to 900 MB. Then I'm going to run some workload. Now I am not telling you what workload I am running and what am I trying to do, but I'm going to simulate some workload which will consume memory, and then we are going to go back to our troubleshooting script to find out where the memory is being consumed. At some point, as memory consumption keeps rising up and we touch 900 and go even slightly beyond 900, you will see OOM exceptions coming in, and that is where we will try to decipher and decode what exactly caused the problem. So let's do this. So first we'll turn on advanced options. Setting max memory is still an advanced option, and set the max memory to 900. Quick warning, do not do all of this stuff on VMs or servers that are important to you, right? If you want to use these scripts and play around, do it in a throwaway VM where you can do all of this stuff with, let's say, checkpoints being turned on, and then maybe you can reset it back. That's what I do, when things go wrong. So, it doesn't cause any kind of losses to anyone. So I'm going to set this to 900, and I'm going to go a bit slow because the demo has to work. Remember the 10th guideline, sometimes these demos don't work. So I need to be careful that I do it the right way. Now max memory is set to 900. Let's go to my troubleshooting script here, and this is what I wanted to run. And I can see that memory is 728 KB. And these are all the memory objects that are showing up the consumption and the clerks. So, okay, so that's there. Now let's go to cause OOM errors. Okay, so I'm going to go to cm command file, and let's go to cd. Can I just directly jump into this folder? Okay. There you go, OM. And what's the file? We're going to cause OOM. So let's do that. Cause OOM.cmd. Now, I'm expecting that. Okay, so I'm using RML utilities here. This batch file is calling ostress.exe, and I'm running some script, creating multiple threads. So what I will expect that the moment we run it, for next few seconds, threads are going to be created, and memory consumption will rise up. And as I said, at some point we will hit the threshold, and then we will get OM exceptions. This is what I'm expecting, and I hope it works. If it doesn't work, I will try again, but let's see. I'm hopeful. So let's go and fire this. This is running. Let's go back to SQL Server and look at memory consumption now. So keep an eye on the total memory being consumed. Okay, so looks like memory is static at 728, which means consumption is not happening. So something is okay. There you go, 730 MB. Let me go back and look into the code. Thread execution has actually started. Beginning execution. Okay. Okay. And now you can see that mem obj cursor exec comes here, which is about 143 MB being consumed. And you can see that now buffer pool is not the highest memory consumer. The clerk is cache store SQL CP, which is for the SQL plans. That is consuming about 153K. So you see suddenly the dynamics have changed. Few other objects are coming on top, right? And let's continue to run it. Wow, now you can see memory consumption has hit 853 MB. Remember, 900 MB is max. You can see memory objects, cursor exec, right? 239 MB. So we are kind of hitting the threshold now in a while. Okay, we have hit the threshold. Now we have crossed over 900 MB. We can see that something to do with cursor is what is happening right now. And cursors, the memory objects that are allocated for cursor execution, this allocation is done from the clerk cache store SQL CP. If I take a break from this script and just show you how many memory objects are there for cursor, let's go and run this. And this is the code that is running, and you can see about 42,000. If I can just zoom in, and I can show you 42,000 objects are created for this cursor execution. This object is called as mem obj cursor exec. So something is going wrong there. But OOM exception has still not come in. You can see this batch file continues to run, but maybe at some point this might hit the limit. Okay, there you go. So let's zoom in a bit here, and you can see that there is insufficient system memory and resource pool default to run this query. This actually is also a message that is related to resource governor. So resource governor behind the scene runs by default, and there is a default pool and there is a default workload group. So if you have not explicitly configured resource governor, all incoming workloads go to the default pool. And this is a error message that is coming up, which means even if resource governor wasn't there, it simply means that now SQL Server Database Engine does not have enough memory to continue running this workload. It has hit its threshold. And you can see what we have done here. We have used clerks and we have used memory objects, right? These are the two DMVs that we have used. And we can see that memory objects, there's something to do with cursor that is happening, and all the allocation is being done by cache store SQL CP clerk. While this batch is on, and let's go and look at this information once more. And you can see 959. Remember, I told you that physical memory usage can go beyond even the max memory for a while, and then it balances out. But there is an interesting thing to note here, that you have paused that workload. Memory being consumed is 959 there, but now you will see that there is no information about cursors anymore here. Even the clerks, for that matter, do not show up here. It's as good as this batch was actually terminated. So, you are kind of closing this workload. And if you execute this again, you can see there's no information of cursors available anymore. Now, this brings us to a very important point here. Memory allocations are so dynamic. This information that you're getting from clerks and objects is very volatile, which means while the workloads were running, I was able to extract information and I got the right information. It was very meaningful. I was able to track that cursor objects are being created, but they are probably not being destroyed. And that is the reason why it showed me 42,000 cursors, right? So what's the scenario right now? So if I go and execute, wow, no more cursor objects, they're all gone. Why? Because the workload was terminated. The batch, that script that was running was terminated. So all the resources are freed up. Memory still, SQL Server still has the memory, the 900 MB, the amount of memory it took from Windows, the engine, the process still has the memory, but because the workload was terminated, all the memory objects were destroyed, the cursor objects were destroyed. And now memory objects DMV, the clerks DMV do not give you any more information. This is critical. This is super critical because the history is lost. This information is not preserved anywhere. And that brings us to a very important point, that if you are implementing some kind of baselining mechanism, it is important to get top 10 clerks or top 10 memory objects into some kind of baseline database with some timestamp, so that you can go back into the history and find out what happened 15 minutes back, or what happened 30 minutes back, or what happened on a specific date and time. That is information. That information is very, very critical, and that process, that approach is very important, because once an OOM error comes up and the client workload and the execution is terminated, a lot of meaningful information is gone, is lost away. So hope this demo was useful to just show you how you can approach troubleshooting with SQL Server Memory. Well, with this, let me quickly get into quickly to summarize what we have seen in these few minutes, last 40-45 minutes, is how SQL Server Memory works. A very high level overview of the nodes, the clerks, and the objects, and how it talks to Windows, and a few things about the guiding principles out there. And then we saw how do you approach troubleshooting. If you're very new to troubleshooting SQL Server Memory, keep a few things in mind, that memory clerks and memory objects give you a whole lot of information, and in most cases they're going to be good enough to tell you what exactly is going on. But the SQL Server Memory world and this troubleshooting of SQL Server Memory is much, much more beyond than just this 60 minutes session. So I hope this is a good head start, and at least you have some information so that you can go and read more, practice more, run a whole lot of scripts that are available on Microsoft websites, and many folks from SQL Server community have blogged about this, and go and read and try out a few scripts. You can go to sqlmaestros.com and download all the scripts and this PowerPoint presentation also, and practice it in some throwaway VM. Well, with this, let's jump over to Q&A. If you have questions, I'm here to answer them. And if you have any feedback, I am available on Twitter, _Bansal. Do put down a few comments, and of course, do tag Data Saturdays at the rate Data Saturdays. A great initiative by our SQL family and people from the community. Well, with this, if you are leaving this session and joining some other great sessions that are coming up, thank you very much for your time. And do not forget to visit sqlmaestros.com. In fact, that's the place where I've put up scripts and demos and links to recorded sessions from as many previous conferences and community events. So maybe you will get a whole lot of good resources. I keep recording a lot of videos. You will find a lot of free videos on internals and performance tuning.